everyone. In the next few videos, I'll discuss the trigonometric identity method. So this method is basically used to solve the integrals that involve product or powers of trigonometric functions. And in order to solve these, we use the identities. So that's why it's called trigonometric identity method. So mainly we're going to discuss three types of integral in the next few videos. The first one is of the form. So sine of mx times sine of nx dx. So when you have two different angles and you have product of sines, or you have the different angles and product of sine and cosine, or you have product of cosine and cosine. And then we'll discuss the form when we have same angle and we have some power of sine times some power of cosine function. And similarly, we will discuss when we have some power of tangent and secant together, or cotangent and cosecant together. So let's start with our first group. So integrals of the form sine of mx times sine of nx dx, or the other products. So these are important group of integrals that we should learn because they arise in the Fourier series, which we're going to do later in this course. And in order to evaluate these integrals, we're going to use these trigonometric identities that we learned in our previous pre-calculus course. So twice of sine of alpha times sine of beta is equal to, so there are two ways you can write this. So if you don't put the negative sign out, you can rewrite this as 2 sine alpha sine beta is equal to cosine alpha minus beta minus cosine alpha plus beta. Just to make it uniform, I took the negative sign out here. So negative 2 sine alpha sine beta is equal to cosine of alpha plus beta minus cosine of alpha minus beta. Similarly, we have, so if you have twice the product of sine alpha times cosine beta, then we have sine alpha plus beta minus sine of alpha minus beta. And similarly, we have the third identity. So we're going to use these identities to solve some problems now. All right, so in this example, we have to integrate sine of 5x times cosine of 2x dx. And if we notice, we can use identity second here because we have sine of alpha times cosine of beta. So in this case, using the second identity, we get, so sine of 5x and cosine of 2x. So alpha we have 5x, beta we have 2x. So it would be half times sine of 5x plus 2x, which is going to be 7x, plus 5x minus 2x. So that is going to be sine of 3x dx. So half times integral of sine of 5x plus 2x. So sine of 7x plus sine of 5 minus 2, which is 3x dx. So this can be written as the sum of two integrals. So we have integral of sine of 7x dx plus integral of sine of 3x dx. Thus, integral of sine of 7x would be negative cosine 7x and divided by 7. Similarly, integral of sine of 3x would be negative cosine of 3x over 3 plus c. So in case you're wondering how did I got these integrals, so you can think of 7x as u, and then differential of 7x will be 7 dx. So it means you need a 7 here, so you will divide by 7. Thus, so therefore, the product of two trigonometric functions can be written as the sum of two trigonometric functions, and then you can calculate the two separate integrals, which will make the problem easier. So let's move to the second form of integral. So integrals of the form sine raised to power mx times cosine raised to power nx dx. So for these integrals, we're gonna use the identities 1, 2, 3 in the list here. So previously we learned that sine square x plus cosine square x equals to 1. And also we learned the double angle formula. So if you have 2 cosine square x, so that is 1 plus cos 2x, or in other words, cosine squared x is equal to half times 1 plus cos 2x. Similarly, sine square x is equal to half times 1 minus cosine 2x. So these are our double angle formulas. So we are going to use these three identities to solve the problems of the type integral of sine raised to power mx times cosine raised to power nx dx. All right, so there are four different cases that can happen. So depending on whether the power is positive or whether the power is even or odd. So first case is if m is odd. So if you have odd powers of sine, so in that case, we rewrite this as so sine raised to power even power and we separate out one power that was odd. So then we use the identity number one, so which is sine square x plus cosine square x equals to 1 to write the sine in terms of cosine, and then we use the substitution u equals to cosine x. So pretty much we will do the same thing in the other cases as well. If the power of cosine is odd, then you write cosine as cosine raised to power even power times cos x, and then this can be written in terms of sine, and then you use the substitution u is equal to sine x. The third case is when both of them are even. So then we can use the identities repeatedly to have the even powers of x. For that, we're going to use our identity number 2 and 3 when both of them are the same. And if both the powers are odd, so either you can use case number 1 or case number 2, which is the case when powers are odd. So let's try a few examples, then it will be more clear. In first example, we notice that so we have the form integral sine raised to power mx cosine raised to power nx dx. And we notice that both m and n are even powers. So this is our case number 3 when both m and n are even powers. So we use identities 2 and 3 to have the even powers. So identity 2 and 3 is our double angle identity. So we're going to use this relationship. So we can rewrite our integrals as, so in place of sine square, we write half of 1 plus 1 minus cosine 2x. So half 1 minus cosine 2x, and in place of cosine square, we write half 1 plus cos 2x dx. So in the next step, we notice that 1 half times half is 1/4, and 1 minus cosine 2x and 1 plus cosine 2x. So we can use the difference of square. So we get 1 minus cosine square 2x dx. Now we can split this into two integrals. So we get 1/4 integral of 1 times dx minus 1/4 integral of cosine square 2x dx. So integral of dx is just x, so we get x/4. And for this one, we have cosine square, so we can again use our identity that cosine square x is equal to half times 1 plus cos 2x. So we get 1/2 1 plus, so angle is 2x, so angle is going to double, so now we can have cosine of 4x dx, which can be written as x/4 minus 1 over 8, and we have integral of dx, and minus again 1 over 8 integral of cosine of 4x dx. Thus we get x over 4, and then integral of dx is just x minus x over 8, and integral of cosine of 4x. So in this case you can again think of 4x as your u, and then your differential of that should be 4 times dx. It means you need a 4 here, so you need to divide by 4. So you can write 1 over 4, and you can write 4 times dx. So this is your du. So we get 1 over 32, and integral of cosine u would be sine u. So sine of u means sine of 4x plus c. So that is our final answer for this problem. So it's always a good idea to recognize what case you're going to work with. So let's take a look at another example. So here we have sine cube x and cosine 4x dx. And we notice that the power of sine is odd. So first step is you split this as even power of sine times sine. So this would be our case 1. So we start by writing sine cube as sine square x times sine x, and then cosine 4x as it is. And in the next step we use the relationship that sine square x plus cosine square x equals to 1, or sine square x is equal to 1 minus cosine square x. So we use this relationship and convert this in terms of cosine. 1 minus cosine square x times sine x times cosine raised to power 4x dx. Now we can rewrite this as two integrals. So 1 times cosine 4x times sine x dx. So that would be your first integral. And then we have minus cosine square x and cosine 4x makes cosine raised to power 6x times sine x dx. So that would be our second integral. So in order to solve these integrals, we recognize that we have cosine function here. So function raised to a power, and then we can make the differential of the function. So if your function is cosine, so then the differential should be negative sine x dx. So in this case, all we need is a negative sign. So we put a negative sign here, and in order to compensate we need to multiply it outside. So similarly here we have cosine raised to power 6, so function has some power, and then the differential should be negative of sine x dx, and we need another negative outside here. So that makes our general power rule. Thus our integral should be, so minus, and then we have function raised to power 4, so integral should be function raised to power 5 divided by the new power. Similarly minus and minus plus, so function raised to power 6, so increase the power by 1, so 7x, so cos raised to power 7x over 7 plus c. So that would be our overall result in the end. So if you have an odd power of sine, so always first rewrite that odd power as even power of sine times sine x, and then change the even power in terms of cosine, and then that will help you to solve the problem. Let's do one more for practice. So in this one, so we notice that, so our general form was sine mx cosine nx dx. In this case, we notice that m is 0 and n is 5, which is odd. So this is our case number 2 when the power of cosine is odd. So now pretty much we're gonna follow the same steps that we did in the previous example. So first we're gonna rewrite our cosine raised to power odd. So separate the even power and another copy of cosine, and then we're gonna use the relationship that cosine square x is equal to 1 minus sine square x. But now in this case, our angle is not x, our angle is 2x. So our relationship becomes cosine square 2x is equal to 1 minus sine square 2x. Using that, here we got 1 minus sine square 2x, the whole thing square, cos 2x dx, because this is cosine square 2x, the square of whole thing. So that's why we plugged in the value and then we did the square of whole thing. So now here this is a perfect square, so we can use the expansion of square. So that would be first term square, so 1 square minus 2 times sine square 2x plus square of the last term, which would be sine raised to power 4 2x, and we have cosine 2x outside dx. Now we can rewrite this as three integrals. So we get integral of cosine 2x dx minus 2 times integral of sine square 2x cosine 2x dx, and the last one we have is integral of sine raised to power 4 2x cosine 2x dx. So now we can discuss all the three integrals. So first, if we think about 2x as u, so u is equal to 2x, it means the differential should be 2 dx. So we need a 2 here. So what I'm going to do is I'm going to add a 2 and I'm going to divide by 2 so that I get this form cosine u du. So we know that integral of cosine is sine. So in this case, we get sine, so half sine of 2x or sine of u, which is sine of 2x. Similarly, in the second one, we can think of u as sine 2x. So we have a function square, so u square, and then the differential of the function should be, so cosine 2x times 2 dx. So again, we need a 2 here, so we can multiply by 2. And so basically we have a 2 here, so I'm just going to bring this 2 inside. So I'm just going to bring this inside together so that we can have this form. So now we have the form a function square and the differential of the function. So this is our general power rule. So we get, so raise the power of the function by 1. So sine cube over 2x divided by the new power, which is 1 over 3. In the last one, again, we have a function raised to power 4. So u raised to power 4. And in order to make the differential here, we need a 2. And I'm going to divide by 2. So we get, so this would be your du. So again, general power rule. So we get, so increase the power by 1. So u raised to power 5. So sine 5 2x over 2 plus c. And now we notice that, sorry, power 5. So now we notice that 1 times 5, 2 times 5 is 10. Thus in the next step we get sine raised to power 5 2x over 10 plus c. So whenever you have odd power of cosine, So write this as cosine raised to power 1 power times one of the cosines left over, and then change the even power to sines, and then split the integrals and solve it in the end. Similarly, we have another group of integrals in which we have tangent and secant, or cotangent and cosecant. So since we know that sine squared x plus cosine squared x is equal to 1, and if I just divide the whole thing by cosine, so I get tangent square x plus 1 is equal to secant square x. So we got the identity 1 plus tangent square x is equal to secant square x, and also they have a relationship. So we're gonna do the same thing, change the power to the even power and then reduce into one of the variables, like one of the other trigonometric functions which are connected by this relationship. And similarly in case of cotangent, so we have gonna use this relationship that 1 plus cotangent square x is equal to cosecant square x. So the procedure is pretty much same as we did in case of the powers of sine and cosine. So again, when we have these two forms, so we have three cases to consider. The both powers can be odd. So if both powers are odd, so we first keep aside a factor secant x, tangent x, or cosecant x, cotangent x. So keep one power of each on the side, and then if you're left with even powers and you use the identities to write even power of tangent in terms of secant and even power of cotangent in terms of cosecant, and in the end you use the substitution that u is equal to secant x or u is equal to cosecant x. So in case you are wondering that why we set aside this factor secant as x tangent x or cosecant x cotangent x, so remember, so if you have u is equal to secant x and you take the differential of this, so differential of this would be secant x tangent x dx. So that is the reason that we keep one of these factors aside, so that in the end we can make the differential of the function easily. So case 2 is when n is even. It means when the power of secant is even or the power of cosecant is even. So I'm just going to discuss it for tangent and secant. So the same rules apply for cotangent and cosecant together. So for example, let's say if n is even, and first thing we do is we put aside a factor of secant square x. So if it is not possible, so then what we do, we change a factor of tangent square x into a term with secant square x. So I'm going to do a problem, then it will be more clear. So after doing this and we use a substitution that u is equal to tangent x. And the last case is when one is even and the other is odd. So we're going to learn these methods later in the course, where we're going to do integration by parts. So only then we can solve it. So let's take a look at this example. So in this one, we have integral of tangent square x secant raised to power 4x dx. So here we notice that our n is even, or the power of secant is even, which is 4. So it means this is our case number 2. So as mentioned in the method, so if possible, set aside a factor of secant square x. So in this case, we can rewrite this as tangent square x, and secant 4x, I'm going to write as secant square x, secant square x dx. So I'm setting aside this factor secant square x. And now, whatever the secant square terms are extra, so we're going to convert those terms into our tangent square terms. So using the relationship that secant square x is equal to 1 plus tangent square x, so we're gonna plug in that value, and now I can split this as two integrals. So the first one would be tangent square x, secant square x dx, and the second one would be tangent raised to power 4x, secant square x dx. So now we notice that here we have tangent is our function u, so tangent, so u raised to power some power, and differential of tangent is secant square x dx. So we have a function raised to some power and the differential of the function. So it means this is our general power form. So we can have, so u square du. So integral of u square would be u cube. So in this case, u is tangent. So it would be tangent raised to power 3 over 3. Similarly, in other one, so we have tangent raised to power 4 and then differential of tangent. So that would be tangent raised to power 5 x over 5 plus c. So now this explains the reason that why we keep a fact like secant square x aside in the beginning, so that we can make the differential of tangent. Let's practice with one more. So next we have when both the powers are odd. So that is our case number 1. So as discussed in case number 1, the first step is you want to keep aside a term of secant and tangent. That's why I'm going to rewrite this as tangent square 2x, and I'm going to keep one tangent separate. Similarly, secant square 2x, and we have a tangent and secant separate. So we keep it so that we get our differential in the end. Then we're going to change the even powers of tangent into secant using the relationship that, okay, so what is the relationship? So tangent square x is equal to secant square x minus 1. Remember we had that 1 plus tangent square x is equal to secant square x. So using this we got secant square 2x minus 1. So that is in place of tangent square. And then we have secant square 2x. And then we have secant 2x tangent 2x dx. Now we can split this as two integrals. In the first one we got secant raised to power 4x, 2x, and then multiplied by secant 2x tangent 2x dx minus, so we got secant square 2x, and then we have secant 2x tangent 2x dx. So now we notice that, so if we take u as secant 2x, so the differential should be secant 2x tangent 2x, and we needed 2 here, so times 2, so 2x dx. So du should be 2 secant 2x tangent 2x dx. So we needed 2 here, so we multiply by 2 and we divide by 2. So now this becomes our du, and this is our u raised to power 4. Similarly, in the other one, so you have u square, and in order to make the differential here, you need 2 times a secant ux tangent 2x, so 1 over 2. So this is your d, this is your du. So using the general power formula, we got half, and then u raised to power 5 over 5. So this means secant raised to power 5, secant 2x raised to power 5 over 5 plus, sorry, minus half, and then secant cube, and then divide by the same new power plus c. So overall we got 1 over 10 secant square, secant raised to power 5 2x minus secant cube 2x over 6 plus c. So we notice that use of trigonometric identities make us help us to solve some integrals, which becomes quite simpler while using the identities. So make sure you revise each of these forms carefully. And I hope you enjoyed this video. Keep watching.